You know how to add two fractions when you're adding 2 over x minus 2 plus maybe 4 over x plus 3. Ne? When you're adding these two fractions, you're looking for the LCD, okay? You look for the LCD. What is the LCD here? We agree it's x minus 2, x plus 3, ne? And then x minus 2 into x minus 2 times x minus 2. They will cancel, so it would be x plus 3 times 2 plus 3. Eh? 2 times x plus 3. And for the second time, this goes through here. It will cancel x plus 3 and left with x minus 2 times 4. Eh? So 4 times x minus 2. Okay. That's how you add fractions. You know this from grade 9. Okay. You know how to add fractions. So when you're adding like terms now, you open the brackets and add like terms now. So you'll see that you'll have 2x plus 4x, which will give you 6x. After you open the brackets and multiply with 3, you're going to have 6. And then this 4 multiply with minus 2, it's minus 8. Eh? So you're going to have 6 minus 8, which is minus 2. Okay. All over a denominator, x minus 2, x plus 3. Yeah? So when you're adding these two fractions, you get this expression. Yeah? So what this on the left, we call them the partial fractions of this expression on the right. Yeah? We're able to take from partial fraction into a single expression. Yeah? And the reverse process, that is what we want to do. Eh? So you'll be given the single expression, and then because you don't have a standard integral of this, but if you can write this in terms of each partial fraction and just integrate each partial fraction, because this is equal to its partial sum of the partial fractions. Okay. So what I mean, let's say you want to integrate 6x minus 2 over x minus 2, x plus 3 dx. You'll see you don't have a standard integral of this, or you may not be able to integrate this, but you're able to put this into partial fractions because this equal to the sum of its partial fractions. So now instead of integrate this, because we don't have its standard integrals, so we just integrate its partial fractions. 2 over x minus 2 plus 4 over x plus 3. No? And then the x, we can just integrate the sum of partial fraction. We'll be able to find this integral. Okay. It's a reverse process that is required, taking from the single expression now into the sum of partial fractions. Before I go in details with integration by partial fractions, but let's learn how to take expressions into partial fractions. Okay. Let me start by giving you the rules of partial fractions. I did this on Monday. Okay. On Tuesday. Okay. Yeah. Yesterday. the rules of partial fractions. We apply partial fraction in algebraic function like a polynomial divided by polynomial functions. Okay. The first rule, it say the degree of the numerator must be less than that of the denominator. The degree of the numerator must be less than that of the denominator. So what they mean by the degree, in your expression, you'll be given a single expression like this. So you need to put them into its partial fraction. But before you put your expression into partial fraction, you check the degree. So the degree, it means the highest power. Okay, degree, the highest power. So the degree of the numerator, they mean the highest power of the numerator must be less than a highest power of the denominator. So the highest power is highest power of x. So the highest power of the numerator here is 1. In the numerator, x is to the power of 1. And the highest power of the denominator is 2. After I multiply the brackets out, so see you have x to the power of 2 as the highest power. All right. So the highest power of the numerator should always be less than the highest power of the denominator. Highest power, it's a degree, so the degree of the numerator should be less than of the denominator always. That's why we can able to put this into partial fractions, okay? Because the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 1 and the degree of the denominator is 2, okay? So you always check the degree, the highest powers. Okay. Okay. This degree means the highest power of x. Okay. And the second rule, this one, if the degree so if the degree of the numerator is bigger or equal to the two of the denominator starts with the long division. So if the degree of the numerator is bigger or equal of the numerator, then starts with the long division. So if the highest power of the numerator is greater than the highest power of the denominator, or it's equal to the of a denominator, and then starts with the long division. Okay, you'll see example that's involving this statement rule. And then the last one, factorize the denominator completely. Okay, factorize the denominator completely. Let's look at this example. So before you put your expression into partial fraction, make sure the denominator is factorized completely, because these prime factors in the denominator determine the shape of your partial fractions. Okay, you see each factors, it's a linear here. Okay, next we're going to look at the linear factors in the denominator. So the linear factor in the denominator each linear gives you a term which is a constant of that linear. As you can see, this x minus 2 give us a constant over that linear, which is x minus 2. And also another term will be given by this prime factor. Since it's a linear, it will give you a constant over that linear. So I'll go in details with this linear factor in the denominator. So you need to factorize your denominator completely, because the prime factor determines the shape, as you see above, determine the shape of your partial fractions. Okay, all right. So I said for now we're going to learn how to put what's happening now. This thing just jam. Okay. We're going to consider the forms of partial fractions that we're going to consider in this course. Forms of partial fractions. The first one, it's a linear factor. Linear factors in the denominator, I just explained above. But let's consider this example. Let's consider the linear factors by this example. Let's say we want to express 3 over x plus 1, x minus 1 into partial fraction, or in partial fraction. We have the expression here, a simple expression. We want to put it in partial fractions. So you check the above rules. In your expression, you check the degree, the highest power in the numerator, it should be less than with the denominator. In this case, the highest power in the numerator, we have x to the power of 0, right? Like 3x to the power of 0. The highest power of x is 0 in the numerator, and in the denominator is 2. You see, after multiply the bracket power out, you see the highest power is 2. That's the degree. The degree of the denominator is 2. So, which means we're able to put this into partial fractions. And that one, you need to make sure the denominator is always factorized completely. So it's already factorized here. So you know how to factorize. So we're not going to be in details with that. So I'm not going to stress you too much about factorization, okay? But you should make sure it's already it's factorized. Okay, so after factorization, you're ready to put this into partial fractions. Let's put this expression into partial fractions. 3 over x plus 1 times x minus 1. I said the linear factors in the denominator determine the shape of the partial fraction of the whole. Yeah, it should be a sum of the each shape that's formed by each linear factor here. So those linear factors are linear, right? So each linear will give you a constant. You don't know the constant. It's a over that linear, the first linear, it's x plus 1. And also this linear x minus 1 will give you another term, which is a form of a partial fraction of a constant. We're going to use b over x minus 1. All right. So each linear gives us each form of a partial fraction each term. Okay. So a form of a linear, it's a constant over that linear. All right. So after you form these linear partials forms, then you need to solve for a and b here. To solve for a and b, always multiply by the LCD. So this is the lowest common denominator. So always multiply by LCD, which is x plus 1, x minus 1. You multiply by x plus 1, x minus 1, both sides there, left and right, okay? So when you multiply with this on my left-hand side, so you'll see this will cancel with all this, so you're just gonna left with 3, and then equal to, multiply this into the right side. So multiply into the first term, it should be a over x plus 1 multiplied by this. You notice x plus 1 cancel with x plus 1. You're gonna have a x minus 1, okay? And multiply this again into the second term. So notice x minus 1 cancel with x minus 1. And then you're gonna have v x plus 1, all right? Okay. So after you form your partial fraction, multiply by the LCD. And then the next step, you need to understand that x can be any number here, all right? So you just choose x first such that it cancels each term or each bracket, okay? You choose x such that it make each term 0 or each bracket 0, né? So if I choose x equal to 1, you see the first term here, 1 minus 1 will be 0, so this term will be 0. Né? So if x is equal to 1, I will have 3 equal to, this is 0, and x is 1, so we're going to have 2b. So the value of b is 3 over 2, all right? And do we have another, because we still need another value of a constant, we already have the value of b here, so we still need another value, which is a. And then again, you think if there's another value of x that cancel one bracket, that make one bracket equal to 0, okay? You see, in my second term, x equal to minus 1, will cancel this bracket. So let's see. When x equal to minus 1, I will have in this expression 3 equal to, if now it's minus 1, this would be minus 2. It's minus 2a in my first term. And here, if x is minus 1, I'm going to have minus 1 plus 1, which is 0. So this term have b, it's 0. So I will able to solve for a here. So a will be minus 3 over 2. Okay. Now I have both constant a and b, and then you stop and then substitute them back here into your expression. Yeah. So 3 over x plus 1, x minus 1 is equal to a over, so my a value is minus 3 over 2 over x plus 1, and plus b over x minus 1. B is 3 over 2 over x minus 1. So what I did here, I just substitute into this expression the value of a and b, value of a and b, as I did here. So these are the partial fractions of this expression. They said express this in terms of partial fractions. This isn't. So won't mark you wrong. If you write it like this, or if you write it like this, you can write this as minus 3 over 2x plus 1 plus 3 over 2x minus 1. All right, it's up to you. But these are the partial fractions. You'll see when you add this partial fraction, you get this. It's just we're doing the reverse process because we know from high school how to add these two partial fractions. We just require these partial fractions. All right. So this is the partial fractions of this z. Let me do another example. Example 2. We want to express x to the power of 3 over x plus 1 x minus 3 into partial fractions. Okay. Solution. You want to express this into partial fraction. What you notice here, the degree of the numerator now is greater than of the denominator. You see the degree of the denominator is 2. You'll see after you multiply the brackets out, x times x squared. The highest power of the denominator is 2 and the highest power of the numerator is 3. So the degree of the numerator is greater than 2. So when the degree, you'll see the point rule number 2 that I gave you above. When the degree of the numerator is greater than of the denominator, or if they are equal, just start with a long division. Okay, so you divide x to the power of 3 over x plus 1 using a long division. But if you're going to use the long division, you don't need brackets, so you may need to clear the brackets out here. This will be x squared minus 2x minus 3. Okay, so we divide x to the power of 3 over x squared minus 2x minus 3. Okay, let's use a long division to do this. So what we're saying here, we're saying x to the power of 3 is dividing x squared minus 2x minus 3. Okay, so we're dividing the expression using the long division. We focus on the highest powers. The highest power here is x to the power of 3. We're going to divide with the highest power term here, which is the first term here. Okay, we only divide the highest powers. Okay, so x to the power of 3 divided by x squared. There we divide the term that has the highest power. So you'll see x to the power of 3 divided by x squared. It's x. Okay, x to the power of 3 divided by x is x. You know the rules of long division. You multiply this x times, what you're gonna do, just multiply all terms. You say x times x to the power of squared is x to the power of 3. X times minus 2x is minus 2x squared. X times minus 3 is minus 3x. We still follow the rules of long division. We need to multiply by minus, put brackets and put minus here to show we minus everything here. And then let's minus this. We say x to the power of 3 minus x to the power of 3. It's 0. We usually put dots if it's a long division, indicates it's 0. And 0, here we have a 0 term which have x squared, so 0 minus 2x squared, so it should be positive x squared. 0 minus 3x, it's plus 3x squared, 3x, sorry. All right. Again, we're saying now we consider this first term again divided by the highest power here. We're gonna keep dividing this term with the first term as long as these have the highest power than what we divide. Okay, here we divide with the s power because it was higher, have highest power, and also here we're gonna divide this as long as it have a highest power or they equal, just divide them. You're gonna stop when this expression here is have a less power than this. Okay, highest power of here. So 2x squared, this is 2x squared. Okay, 2x squared divided by x is positive 2. 2x squared divided by x squared, we only consider the highest powers, is 2. And then you know the rules. With this number that you get here, you multiply everything here. So 2 times 2x squared is 2x squared. 2 times minus 2x, it's minus 4x. And 2 times minus 3, it's minus 6. Okay. And then rules of long division, we need to multiply by minus here, put brackets and put minus here. And then again, add like times 2x squared minus 2x squared would be 0, and 3x minus 4x, so it would be 3x plus 4x, which would give you 7x. And then we have 0 here, constant, minus 6, so 0 plus 6 is 6. Okay, and now we will say we're going to keep dividing up until this highest power here is less than of this. So now we can divide this with x squared and then we stop. Okay, so now x to the power of 3 over x squared minus 2x minus 3. When we x to the power of 3 divided by this, the answer by long division is always gonna be this, is x plus 2, and then plus the remainder. The remainder, you was gonna say this divided by this, but you can't divide because this have a lost power. So you're gonna say 7x plus 6 divided by x squared, but you couldn't divide. Okay, so now with the long division, this x to the power of 3 over x squared minus 2x minus 3 is x plus 1 plus 2, and then 7x plus 6 over this. So doing a long division when the highest power is greater than of the denominator, because it helps us because we can't put this like this in partial fractions. We're able to put this in partial fraction if this have the lowest power than the denominator. If it have a highest power than its denominator, we start by long division, and then you're gonna get something like this. The first sometimes it will be something that we'll able to integrate, and then this last term we couldn't divide, but the next thing, the highest power in the numerator is now less than of the denominator, right? So we're able to put this last term into partial fraction. So we just use long division to write this into some few terms which we're not going to be worrying about because we're able to integrate, and some other term which we're able to put it into partial fraction. Okay, so the next step after applying the long division, you take this term which require which will require to put into partial fraction. So we're gonna come back into this whole thing. But now let's borrow this term and put it into partial fractions. Okay, because we want everything completely in partial fractions. Okay, let's take this term now here, this time, This is the term 7x plus 6 over x squared minus 2x minus 3. Let's put it into partial fractions. You see the numerators have the lower degree than the denominator there. We find, but we just need to factorize completely a denominator. We already know the factors here. It was x plus 1, x minus 3 now when you factorize this. When you put this into partial fractions, each factors in the denominator determine the shape of the partial fraction. Since it's a linear, it will be a constant. Let's say it's a over that linear. The first linear is x plus 1. And another term, it will be a constant over a second linear, x minus 1, 3. All right. After this, we use b, sorry, because we already use a here. Another constant b. So solve for a and b. Always just follow the same step. You just multiply by this LCD. In this case, it's x plus 1 and x minus 3. Yeah? So on both sides, you see when you multiply on the left-hand side, they would cancel. Okay. So you're going to have 7x plus 6 equal to, and multiply in the right-hand side, start with the first term. You notice when you multiply with this x plus 1 with x plus 1 will cancel. We're going to left with x minus 3 times a, x minus 3 times a, plus b, x minus 3 will cancel, will be x plus 1 multiplied by b, x plus 1, it's multiplied by b. Yeah? So after multiplying with the LCD, so again, think of the value of x that will cancel each term. So we're going to start with the value of x equal to 3. Yeah? When x equal to 3, we'll cancel the first term. So when x equal to 3, let's see, in the left-hand side, it will be 3 times 7. 21 plus 6 is 27. And this will be 0 because it's cancelled. So 3 plus 1, it's 4. So we're going to have 4b. So we find b. B is 27 over 4. All right. We still need the value of a. Again, think of another value of x that's cancel one term, or make one term, another term equal to 0. It's x equal to minus 1. It will make this term equal to 0. So when x now equal to minus 1, when we substitute x equal to minus 1, we're going to have minus 7 plus 1, which gives us minus 1 on the left-hand side. When we put minus 1 here, it will be minus 4a. When we put minus 1, this will be 0. So automatically we're going to find the value of a. Value of a is b1 over 4. No? We have the value of a and value of b. All right. So after you find the value of a and b, substitute them back here. Okay. So here, 7x plus 6 over x plus 1 and x minus 3 is equal to, you see here, from here, 7x plus 6 over x plus 1 is equal to a, but your a value is 1 over 4, so it will be 1 over 4 over x plus 1. 1 over 4 over x plus 1 plus second term is b over x minus 3, yeah? Or b is 27 over 4. 27 over 4 over x minus 3, yeah? Okay. So this is our x, the term that we borrowed from here, that we wanted to put it into partial fractions, okay? All right, let me rewrite this. We said x to the power of 3 over x plus 1, x minus 3. After long division, this was x plus 2 plus 7x plus 6 over x plus 1 and x minus 3. No? Okay, what we're doing now, we're putting this into partial fractions, and then we did here, this is the partial fractions of this last term. So now instead of this, we're just going to substitute its partial fraction. So this is be x plus 2. So instead of this, let's put 1 over 4 over x plus 1 plus 27 over 4 over x minus 3. Right. So now these are the partial fraction of this. We use the long division and put them in this form, and then we take this last term because we're able to take this into partial fraction and put it into partial fraction. If you like, you can write this as 1 over 4 x plus 1 plus 27 over 4 x minus 3. Okay. Yeah. Okay, that was the first form of the partial fraction. When you have a linear, just know the linear give you a constant of a linear. That was the main focus on this, and then just solving the constant. Okay. So a quadratic form. Quadratic factors in the denominator. We're going to look the quadratic factors in the denominator by this example. Let's say we want to express x squared plus 3 over x times x squared plus 2 in partial fraction. We want to express this expression into partial fractions. Okay, it's a quadratic. So solution, let's take x squared plus 3, this same expression x here, x squared plus 2 into partial fraction. You always need to check the degree because you may need to start with the division, long division. And the degree of the numerator is 2, and the degree of the denominator is 3. The highest power on the denominator is 3, and the highest power in the numerator is 2. We find because the degree of the numerator is less than of the denominator. And next, make sure the denominator is factorized completely. This is already factorized. We took the common factor. We can't even factorize this x squared plus 2. Okay? We agree? We can't factorize x squared plus 2. But the thing here in the denominator, we have a factor which is a quadratic. So I told you the factors on the denominators give us a shape of a partial fraction. We already know from the previous example, we did the linear. A linear factor give you a constant over a quadratic. Okay, a constant over a linear, that linear. All right. So, okay, let's consider this example. So the partial form of this, we have x is linear, x plus 0. As long as linear is, you have the power to the power 4. So this linear x will give us a shape of a partial constant over that linear, which is x. Okay. This x would give us a constant over that linear, which is x, plus another factor, and this factor is a quadratic. A quadratic will give you a linear over a quadratic. Yeah? A linear will give you a constant over a linear. A quadratic will give you a linear over a quadratic. Yeah? So just know quadratic give you a linear form is bx plus c upon a constant x plus c over that quadratic. Yeah? Just know quadratic will give you a form of a linear over a quadratic. Okay, that's the only main aim here. All right, and next step is just following the same step of solving a, b, c here by multiplying by this LCD. We're multiplying by x squared plus 2. Multiply on the left hand side, you'll see they will cancel. So this will be x squared plus 3, because this will cancel, equal to, when you multiply this into the first term on the right hand side, you'll see x will cancel with the x. This will be a x squared plus 2 plus, when you multiply this with this, x squared plus 2 will cancel, so it will be x multiplied by bx plus c. All right. Okay, we're solving for constant. We're following the same step. Next step, you're thinking of a value of x, because x can be any number, right? That can cancel or make one term equal to 0 in this expression. Okay. So each term if we made x equal to 0, this term will cancel, right? So let's see when x equal to 0. The left-hand side will be 3, 0 plus 3 equal to 0, 2a. When x is 0, everything will be 0 here. So automatically, we see the value of a will be 3 over 2. Okay. Do we have, because we still need the value of b and c. So as you can see, we can't think of any value of x that can cancel each term. So we're just taking any value of x because it's by inspection, x can be any number. We know we're able to solve some constant if a value of x cancel one of the other terms. But if you can't think of any value, it doesn't mean you can't solve for other constant. So you need to equate the coefficient. If those two expressions, they say they're equal, okay, it means the sum of the coefficient of x on the left hand side equal to the sum of the coefficient of x for each term on the right hand side. So the coefficient of x on the left hand side equal to the sum of coefficient of x on the right hand side. What is wrong now? All right, I'm sorry about this. Okay. So if you can't think of the value of x that cancel each term, just equate the coefficient of x's. So we need to see from here what are the coefficients of x's. So we may write this nicely just to see the coefficient of x and x squared and constant. So let's multiply x. As long as we see the coefficient of x as x squared and constant, and if we multiply x here, it should be cx. Now from this expression, we see the coefficient of x's, so we just equate the coefficients, start with the highest power coefficients, which is, in this case, we have x squared there. Highest power of x is 2 x squared. So coefficient of x squared, it's 1. It will be equal to the sum of a coefficient of x squared on the right hand side if this thing they said they're equal. So coefficient of x is a plus b. Yeah. Okay. So sum of the coefficient of x squared on the left hand side equal to the sum of the coefficient of x squared on the right hand side, right? And after you form the equation in terms of constant here, always check back the constant you already got from the previous. Okay, you see we already find the value of a, so just substitute a here. You see b is equal to 1 minus a, and then it should be 1 minus 3 over 2. This will give you minus 1 over 2. So this is the value of b. B equal to minus 1 over 2. Okay. Let me indicate my constant. I already found 2. Okay. I still need to find from my expression here. I found a and b. I need c. So you need to equate the next power coefficient, which is x, the coefficient of x here, the coefficient of x here. Okay, let's equate the coefficient of x here. Let me write it down here. Here. You see the coefficient of x, we're looking in this expression here. Now the expression is plural, because sometimes it looks nice. The coefficient of x here is 0, is equal to the sum of coefficient of x here, which is the only coefficient of x is c here. So 0 equal to c. So the value of c is 0. So when we equate in the coefficient of x, we notice on the left hand side is 0 equal to c. Yeah? So the value of c is 0. So we find the value of c. After finding all these values here, substitute them back here. Let me write this expression in terms of partial fraction and substitute their constant. So this x squared plus 3 over x squared plus 2 in terms of partial fractions, a over x, it's a over x, our a is 3 over 2, over 2 over x. We substitute this constant that we got here, this 3 constant, and mark with the red into the expression here. A over x, and then bx plus c. B, value of b is minus half. Bx plus c. This is plus. B is minus half. X plus c, remember c was 0 over x squared plus 2. So these are the partial fraction of this expression. So you can write it nicely. 3 over 2x minus x over 2x squared plus 2. All right. There it. So we wrote this function with a quadratic factor in terms of partial fraction. So the only aim here was to know the factor of this quadratic factor. A partial form of this quadratic factor is linear over a quadratic. That we did here. Okay. All right. And the last part, and then we go to integration. It's when we have a repeated factors. When we have a repeated factors, let's look at this example. Let's say we want to express this expression (3 over x times x plus 1 all to the power of 2. We want to convert this expression into partial fractions. Okay. A solution. We take the same expression and put it into the form of partial fractions. We said the denominator determine the forms of the partial fractions, okay? We have x we treat as a linear. If you have a linear, it will give you a form of a partial fraction which is a constant over this linear. In this case, this is x, it's a linear. And the second factor is x plus 1, but x plus 1 it's repeated. X plus 1 squared it's same as x plus 1 times x plus 1. So if you have a repeated factor, you're using the form of that factor. So we have a linear, but it's repeated. So the form will be a constant, let's say it's b now, over that linear, it's x plus 1 to the power of 1. And you're gonna repeat it another form of a linear, which is a constant, but now that linear is to the power of 2. So you're gonna keep adding the term of the form of the partial fraction of that linear up until this linear is to the power of this number. In this case is 2. Okay. So okay, let's say if we have 3, I'm not going to change my problem, but I want us 3 let's say x plus this linear. We started with this linear x. It gives us a constant over that linear, and x plus 1 to the power of 3. It's a repeated factor, which is x plus 1 times x plus 1 times x plus 1. So it would give us a constant of x plus 1 to the power of 1, and repeat another factor, a form of the partial fraction. It's a constant over x plus 1 now to the power of 2, and then you're going to repeat the form up until is to the power of this number 3. Ne? So now if it's to the power of 3, you need to add another form, so which would be x plus 1 to the power of 3 in this case. Ne? It's only when you have x plus 1 to the power of 3, so this would be the form of the partial fractions. But our problem have x plus 1 to the power of 2, so let's return this. This is 2, okay? We don't have this. So when x plus 1 is to the power of 2, we're gonna repeat up until this linear factor is to the power of this number. In this case, is 2. Okay. So these are the form of the partial fraction. Once you form the form of the partial fraction, you need to solve for a, b, and c this constant. And the first step, when you're solving this constant, you multiply by x. This LCD, LCD is x times x plus 1 to the power of 2. So I want you to solve for a, b, and c as a try this. I already did in the previous video and show you how to solve the constant, but just to give you a hint, you multiply by this LCD. So when we multiply on the left hand side, they will cancel. We're going to have 3 equal to, in the first term on the right hand side, when we multiply, x and x cancel, so it would be a x plus 1 squared, and in the second term, x plus 1 would cancel with 1x plus 1, so it would be b x plus 1. And when you multiply this to the right last term, you see x plus 1 squared cancel with x plus 1 squared, so it would be cx. Okay. Please continue and solve for a, b, and c. Okay. Just to give you the answers, you can check your answer after you solve this. Mina, I found that a was 3 and b was minus 3 and c was also minus 3. Okay, so these were the values of this constant. Okay, but the main idea here was to teach you if you have a repeated factor in the denominator, that's how you treat the repeated factors. So what's happening? What is the form of a partial fraction if we have a repeated quadratic form? For example, okay. Let's see if we have let's see if we have a repeated quadratic in the denominator. As you can see, we can put this into partial fractions because the highest power in the numerator, which is 0, is less than the highest power in the denominator. which is, I think, x to the power of 6. Yeah. So let's put this in a form of partial fractions. So we want to see if we have, what is the partial form of this expression if we have a repeated quadratic form. We have x squared plus 1 times x squared times 1. So x squared plus 1, it's repeated, that's quadratic. So here, x squared we can treat as if we have x that is repeated twice. X is a linear, so we have a repeated linear. So when we have a repeated linear, we have a constant over that linear to the power of 1 plus another constant, which is b over that linear now to the power of 2, and then you stop up until this linear is to the power of the same number. And go to the quadratic. We have a repeated quadratic. A repeated quadratic is going to be a quadratic form. Quadratic form give you a linear. In this case, let's see x plus d over that quadratic x squared plus 1 all to the power of 1. And then since the quadratic is repeated twice, so you're going to add another linear, which will be e x plus f. This is linear over that quadratic now. This quadratic will be to the power of 2. And now since 2 is equal to 2, so you stop. If it was to the power of 3, you was going to add another term. That's up until to the power of 3, okay? But since we have 2, we stop when the denominator is to the power of 2, okay? So this is a form of a partial fraction of this expression. So the next step was to solve for a, b, c, d, e, and f. So I wouldn't ask you to solve such complicated with many constant like this. 2, 4, 6 constant, okay? So yeah, but that's how but it's very important to know how to write the form of partial fractions, okay? It will help you when you do the examples. So now let's go to integration by partial fractions. Okay. The example that we looked at was they want you to evaluate the following integrals. In class, I gave you those two problems, and I did only A, and I asked you to do B as exercise. This exercise, these problems with the examples on your notes, study link. You have solution there, you can check them. If you got striking, but I'll give you a solution for A. But please start by trying B before you check the solution on your study notes. This is x squared. Okay, you are given these two examples. I will do A. Please try this one as an exercise. But let's do A together. So we want to find the integral of this A. So you see, you don't have a standard integral of this, but now you understand. If you can take this expression into partial fractions, then you'll be able to just integrate each partial fraction then to integrate this because it looks complicated. You don't have a standard integral for this, okay? And again, your first step is to check the degree of the numerator is always should be less than of the denominator. Ne? You see the degree of the numerator is 2, the highest power is 2. And the degree of the denominator is 4, the highest power in the denominator is 4. So the highest power in the numerator should always be less than. If it's equal or the degree of the numerator is greater than of the denominator, you start by long division. Eh? In the first recorded lecture, I show you how to use a long division, okay? So here, first, let's take this expression and put it into partial fractions before we integrate. X squared minus 12x plus 39 over. So in the denominator should be factorized completely, right, before you put it into partial fractions. So the first step of factorization is to look for common factor. So what is common in the denominator? You'll see it's x squared over, and then x squared minus 4x plus 13. Okay, so you need to factorize the denominator completely. You check into my factorizer. Can you factorize this quadratic thing? Do you have factors to factorize this? Factors of 13, that if you multiply, you get 13, but when you add them or find the difference, you get this minus 4x. No. So we can't factorize this quadratic. So let's just go straight and put this into the form of partial fraction. A form of this expression will be determined by the denominator factors. So you see we have x squared. Take as if we have x that is repeated twice, x times x. X is the linear, so it's going to be a constant over that linear x plus another constant, since this factor is repeated twice, that's linear to the power of 2, then you stop, okay? When this linear is to the power of the same number, right? And then plus, again, this will give you a partial form of a linear over a quadratic. So a linear will be cx plus d. This is linear over that quadratic. Because the quadratic factor in this denominator gives us a linear over a quadratic. All right. Now, this is a form of the partial fraction of this expression. That was your first step. So the second step is just to solve this constant, A, B, C, and D. So when you solve this constant, you multiply by this LCD. LCD is always going to be this, x squared minus 4x plus 18. You multiply by this expression on the left hand side and also on the right hand side. So let's start by multiplying with this expression on the right hand side. You see it will cancel with this. This is the same thing. So we're going to have 4x squared minus 12x plus 39. When we multiply on the left hand side, because of the space, let me rewrite this. Let's multiply this to the left hand side. We said it's gonna cancel, so we're going to have 4x squared minus 12x plus 39. I don't know. Equal to, when we multiply now this into the right hand side, start with the first term. You see 1x here will cancel with this x. So it will be a times this one x that's left, and then multiplied by this quadratic, which is x squared minus 4x plus 13, and then plus multiply this into the second term. So you see x squared cancelled with x squared. We're going to have b x squared minus 4x plus 13. And again, multiply this to the third term. The quadratic will cancel, so it will be x squared. X squared, just multiply this cx. It's multiply cx plus d. Okay. So always after multiplying this LCD out in the left hand side and right hand side, think of the value of x that cancel each term. That will make each term equal to 0. So you see x equal to 0 will make this term equal to 0 and also this term equal to 0, right? So when x equal to 0, when we substitute x equal to 0 here, we're going to have 39, and this will be 0. If we substitute 0 here, we're going to have 13p. And when we substitute 0 here, we'll make everything equal to 0 here. So 13p, and then if you solve for b, we find that b is equal to 3, yeah? Because when you solve for b divided by 13 on both sides, 39 divided by 13 is 3, yeah? So this is the value that we already found of the constant. Because sometimes it looks messy, let me use a red to highlight the value that I've already found. We still need the value of a, c, and d. But the problem now, we can't think of the value of x that can make each bracket equal to 0. But we know x can be any number, but that was just by inspection, because we able to find some constant if we make some brackets equal to 0, right? Okay. Now, since we don't have values of x that we can cancel each term, so let's equate the coefficients. The coefficient of x on the left hand side equal to the sum of coefficient on the right hand side. If they say these expressions are equal, so the sum of coefficient on the left hand side should be equal to the sum of coefficient of x on the right hand side there. So to see clear what are the coefficients of x, we need to multiply x here so we can able to see what are the coefficients of x is there. All right, so let's do that here. We look at this expression, we want to see the coefficients of x, okay? So let's listen the left hand side. This is 4x squared minus 12x plus 39 equal to a. I'm multiplying x inside here in my first term. As long as I see the coefficients, I don't have to multiply a, but you can multiply also a inside if you like. So this is x to the power of 3 minus 4x squared plus 13x. When I multiply to the first term, b, I can see the coefficients here, x squared. I'm returning everything as it is, plus 13. And here in the last term, I'm multiplying x squared inside there. So this would be plus cx to the power of 3 plus dx squared, okay? So I'll be looking now, so I'll be working with this expression, okay? Let me work with this expression. This is the expression where I'll be equating the coefficients of x. So when I'm equating the coefficients of x, I start with the coefficients of the highest powers of x. If you check here, it's x to the power of 3. So let's equate the coefficients of x to the power of 3. Ne? The sum of the coefficient of x to the power of 3 on the left hand side equal to the sum of the coefficient of x to the power of 3 on the right hand side. So you see it's 0 on the right hand side. We don't have x to the power of 3 on the right hand side. And on the right hand side, it should be a coefficient of x to the power of 3 plus c, another a coefficient of x to the power of 3, 3, x to the power of 3. So always check if you can constant that you already found from above. We only have b, so continue and formulate another formula, equates another highest power coefficient, which is x to the power of 2. Okay, coefficient of x to the power of 2 on the left hand side is 4 equal to the sum of coefficient of x squared to the right hand side, which would be minus 4a. If I multiply minus 4a, and then plus b, and then another coefficient of x squared is d. Okay. Again, check which constant you already have here. You see, I only have b. I was marking the constant that I already found with the red, so b. So if b is 3, let me substitute 3 here. After substituting 3 here, let's transpose this 3. So it's before minus 3, which should give us 1, equal to minus 4a. We transpose b, which was 3, and then plus d. Yeah? So a and d we don't have, so yeah, we stuck. So we just continue and equate a next coefficient, powers coefficient of x. So here, and next power is x to the power of 1. X to the power of 1. So let's look at this experiment. X to the power of 1 on the left hand side, the coefficient of x is minus 12, equal to the sum of the coefficient of x to the right hand side. You see it to be 13a. 13a. And here, let's check. You see we have minus 4b. Minus 4b, the coefficient of x. Minus 4b. Okay. So here, again, you check. So far, we only have the value of b. B is 3. So if you substitute b equals to 3 here, you're going to have minus 12, 13a, minus, if b is 3, this will be 12. So we'll see that a equal to 0. Okay. If you solve for a, this will be plus, so it will be 12 minus 12, 0. And then when you solve for a, you'll find a is 0. So far we have the value of a and b. B is equal to 3. Okay. So again, once you find the constant, go back to those formula at Wenza in the previous step. So you see a equal to 0. If a equal to 0, this will give us c equal to 0. We find now the value of c equal to 0. And then a equal to 0. If we substitute here, it will give us d equal to 1. And then now we have also the value of d. So from this expression, we're solving for these values of these partial forms, constant a, b, c, d. We find that value, the value of b is 3, value of c is 0, and value of d is 1, and value of a is 0. So here, let me rewrite this expression, because down here, and substitute these values of this constant. So Oh no. Four x squared minus 12x plus 39 over x to the power 4 minus 4x to the power of 3 plus 13x squared. In partial fraction, we said is a over x plus, I'm rewriting what is on top after we form the partial fractions. This was the partial fractions of this expression. Okay, and we found the values of this constant. As you can see, the value of a is 0. It will make this 0. And the value of b, let's check the value of b. The value of b was 3. It was 3. So let's substitute the value of b, and value of a was 0. So the first term here, it should be 0 because the value of a is 0 and value of b is 3. So we have 3 over x squared plus, go to the third term, c and d. Let's start c and d. What are the value of c and d? You see c equal to 0 and d equal to 1. C equal to 0, it will make this 0 and d equal to 1. So you're going to have 1 over x squared minus 4x plus 13. All right. So these are the partial fractions. These are the partial fraction of this expression. And then after you find the partial fraction, go back to your question. We want to find the integral. The question was want to find the integral of this. X to the power 4 minus 4x squared plus 13x to the power 13x squared dx. Because I said we don't have a standard integral of this, but we're able to put this into its partial fractions. So now instead of integrating this, we're just going to integrate its partial fractions because they are equal. So we just substitute its partial fraction instead of this. 3 over x squared plus 1 over x squared minus 4x plus 13 dx. So let's integrate this. You see here, before we integrate, we can write this as x to the minus 2 plus, this is a constant of a quadratic, and then we need to complete the square. So when we complete the square, I assume you know, if you read you were present in class or you look at the video, I did a recorded lecture on integration by complete the square. This was 9, but 9 we need to write both terms in squared. Okay, so I just complete the square of this here. So here, when you're integrating this, the integral of the first term is 3x n plus 1 over n plus 1. So this will be minus 1 over minus 1 plus. So we want to integrate this. So you need to choose z. You set z is equal to x minus 2, and a will be a constant, which is 3. So we have 1 over z squared. We choose z such that it's a function of x. That's why we said it's x minus 2. We have 1 over z squared plus a to the power of a squared. So we want to integrate 1 over z squared plus a squared. We want to integrate 1 over z squared plus a squared. dz. Okay, this is this integral of this form. After you're choosing z and a here, you're gonna have 1 over z squared plus a squared, which is this formula. If you check this formula, it will be given to you. The standard integral of this is 1 over a tan inverse of z over a and then plus c. Okay, this thing when the clean. Okay, so now you'll be able to integrate this after you're choosing your z and a, and then now you'll see which formula you're going to use. So the integral of this form is 1 over z squared plus a squared. The integral is 1 over a. 1 over a, you set your a is 3. Substitute to this formula, right? And then tan inverse of z. If you check your z, you set your z is x minus 2 over a. If you check your a was 3, and then plus c. Yeah? So now you see we're able to integrate our problem now. Yeah? This is our problem. We just to summarize it, we didn't have the standard form. We put this into partial fraction, and then after putting into partial fraction, just integrate. We notice to integrate the second term, just require integration by complete the square. We completed the square here, and then we choose z and a just to have an idea which formula we're going to use. You see this was z and this was a, so we want to integrate anything that is in the form of 1 over z squared plus a squared. If you check the formula of z squared over 1 over z squared plus a squared, it's 1 over a tan inverse of z over a plus c, yeah? And we use this formula so to evaluate this. So this integral would be 1 over a. Our a we choose to be 3 tan inverse of z. Z is x minus 2 over a, which is 3, and then plus c. Yeah? This is the answer. So it's up to you if you want to continue here and just say minus 3 over x plus 1 over 3 tan inverse of x minus 2 over 3 plus c. Okay, that's the end. And please try B. Try B. And you can ask me in class on Monday, or if you're still stuck, or I think this was examples on your study notes under interpretation by partial fractions. B, I think there's a solution also there. So yeah, thank you.